Let us discuss one more concept about what happens when an electric dipole is placed in an electric field. So we have already seen the dipole experiences a torque. So torque will have a twisting effect or rotating effect. So dipole tends to rotate inside a uniform electric field. So there is no translatory motion, but there can be rotatory motion. So in order to keep the dipole in a particular orientation, we need to do some work. So that work can be appearing as the potential energy of the dipole. So let us see to the details of that. When an electric dipole is placed in a uniform electric field, it experiences a torque and it tends to align in such a way as to attain stable equilibrium, because any system wants stability. So this dipole is in the electric field, it has to be stable inside the field. Till then it will rotate and it will get aligned to the stable position inside that electric field. It is like when we freely suspend a magnet, it will rotate many times and finally it will align in the north-south direction. That is a stable position with respect to Earth's magnetism. A freely suspended bar magnet will get aligned in the north-south direction. That you already know. Electric dipole is something like this bar magnet only. So it will get aligned to a stable position in the electric field. So we have this dipole. Dipole in the electric field. So initial position, initial orientation of the dipole is theta 1. It is making an angle theta 1 with the electric field. So it will be twisted to some angle d theta from that particular position. Earlier it was making an angle theta 1 with the electric field. Now we are twisting it by an angle d theta from that position. So that now total angle will be theta 1 plus d theta. This angle theta 1, from that position we are twisting it to an angle d theta. For that purpose, work required will be dW is equal to tau d theta. Work done is we have to do work against the torque. So work done in rotational mechanism, that is given by torque multiplied by angular displacement. It is like F is equal to force and displacement is equal to x, and work is equal to force multiplied by displacement. Similar to that, torque and angular displacement, their product will give work in rotational mechanics. So dW is equal to tau d theta. So in order to twist or rotate the dipole through a small angle d theta, work required is dW is equal to tau d theta. And tau, substituting for tau, it is equal to p sin theta, because tau is equal to P cross E, magnitude of torque, is equal to P sin theta. And suppose Now the angle made by this dipole with the electric field is theta 2. Earlier it was theta 1. Now after twisting through some angle d theta or many such angles, now it is making an angle theta 2 with the electric field E. In that case, what total work required is given by integrating this dW. So W is equal to integral of dW from where? From initial orientation theta 1 to final orientation theta 2. That's why it is written like this. W is equal to integral from theta 1 to theta 2 p sin theta d theta. And it will be given by p cos theta 1 minus cos theta 2, because integral of sin theta d theta will be minus cos theta plus some constant. But then when we are taking it from theta 1 to theta 2, this constant will be absent. So if you are putting it as theta 1 to theta 2 sin theta d theta, then this will be equal to minus cos theta between the limits theta 1 to theta 2. So substitute. First you have to put theta 2, then theta 1. So minus cos theta 2 minus cos theta 1. You have to put upper limit, then lower limit, and subtract the values. Okay. Here two minus are coming together, therefore that will become plus. So it will be minus cos theta 2 plus cos theta 1. That's why it is written cos theta 1 minus cos theta 2. Minus cos theta 1 plus cos theta 2. So W is equal to P cos theta 1 minus cos theta 2. And if potential energy is arbitrarily taken 0 when the dipole is at 90 degree, then potential energy is rotating the dipole and inclining it an angle theta is. Suppose theta 1 is equal to 90 degree and theta 2 is equal to theta. That's what it means. If theta 1 is equal to 90 degree and theta 2 is equal to theta, in that case this equation will become P cos theta 1 is 90 degree, so cos 90 will be 0, and theta 2 is equal to theta, so it will be cos theta. It will be PE multiplied by minus cos theta, so it will become minus PE cos theta. So this will become cos 90 minus cos theta, so it will be just minus cos theta. If in this case, if theta 1 is equal to 90 degree and theta 2 is equal to theta, this will become, this term in the bracket will become cos 90 minus cos theta. So it will be minus cos theta because cos 90 is equal to 0. So you are getting PE multiplied by minus cos theta, or it is minus PE cos theta. This can be written as PE cos theta. P is a vector, E is a vector, and you multiply with the cos theta, you are getting it as P dot E, dot product of two vectors. We know that A dot B is equal to AB cos theta. So if you are seeing AB cos theta, and if A and B are vectors, you can write it back like this. So P cos theta can be written as P dot E. P cos theta can be written as P dot E, because P and E are vectors. So there can be many cases. If theta is equal to 0, then U is equal to minus P, because cos theta is equal to 0. Cos 0 will be equal to 1. Therefore, this will become U is equal to minus PE. So this is stable equilibrium position. That is a natural position of the dipole in the electric field. That is stable most position. If theta is equal to 90 degree, then U is equal to 0. Potential energy will be 0 in that case. Potential energy of the dipole will be 0 when it is aligned perpendicular to the electric field. If theta is 90 degree, that will happen. Potential energy is 0. And if theta is equal to 180 degree, then U is equal to PE. You see, value is very high. Potential energy is very high in this case. It is U is equal to PE. When potential energy is maximum, it relates to instability. So that alignment is called unstable equilibrium. So there are three conditions. Special cases we are discussing about the alignment of dipole in an electric field. When it is aligned exactly with when the dipole moment is aligned exactly with the electric field, then potential energy is minimum, so it is in stable equilibrium. But if the dipole moment vector is making angle 90 degree with the electric field, the potential will be 0. But if dipole moment is opposite to the direction of the electric field, then it tells about instability, or it will be the dipole will be in unstable equilibrium. Hope it is clear to you. Please go through this video 2 or 3 times. This can be asked as a 3-mark question. What is the work done on an electric dipole in a uniform electric field? So please be careful about arriving at the equation and all.